Okay, so welcome to the virtual session. We are starting right now, which consists of 2 talks. And we are starting with the first one, which is actually a merged talk about privacy amplification and error exponents. So it's a very information theoretic talks, and we have 2 very well-known speakers here. So it's a great pleasure to have Frédéric Dupuis first on the first part, and then afterwards we switch to Ke Li for the error exponent part. So be prepared for a lot of entropies and in particular also sandwiched Renyi divergences and things like this. So please, Fred, go ahead.
Okay, so thank you for the introduction. So yeah, I'll be talking about 2 problems: private simplification and decoupling, and without smoothing. So let me just begin by So let me begin just by introducing these 2 problems before I talk about what I do with them. So the first one is private simplification. So many of you are probably familiar with it. So here's the basic picture. So we have a bipartite state, CQ state. So X is classical, E is quantum, and we think of it as E is the quantum system that some adversary has, and it's information about some string X. And what we want to do is we want to process X so that we get something that is uniform and independent from whatever the adversary has here. And more precisely, what I mean by processing it is that I'm going to take a hash function at random from a family of hash functions, and then I'm going to apply it to X, produce Z at the output. And then I want something that looks like this here. So uniform on Z, tensor product with whatever we have on E here. And the choice of hash function is something that we think of as being public, so that the adversary has it at the end of the protocol. So formally, what this looks like is, well, so here's the process written down as a CPTP map. And what we want at the end is that the expectation over the choice of hash functions here of some distance measure between what comes out of the protocol and the ideal state that we want. So we want this to be small. And what do I, so and small, there are 2 parameters that are going to come into to the bound here on the right hand side. The first parameter is the size of the output here. So the size of Z is going to be something that matters here, because the more bits we try to extract from it, the harder it is. So a bigger Z is going to make this bound bigger. And the second one is how much knowledge Eve had about X in the first place. So there's going to be some sort of distance measure, or some sort of entropy measure of X given E here. So this is like a measure of the amount of information that Eve has about X. And here I put a question mark because the choice of the particular measure of information here is going to be important. And one important case here is the case where rho is IID, so where X is actually a tensor product of 1 to n. E is also a tensor product, and we have the state looks like this here. Decoupling is basically the fully quantum version of this. I'm not going to talk much more about it, except saying that all the results I'm going to talk about essentially also apply to decoupling, more or less unchanged. But I'll be talking essentially only about private simplification. So back to this question of entropy measures. So I said that we need some sort of entropy measure to measure the amount of information that's in X given E. And here are a few choices that we might consider. So the first one is the best known one, is the von Neumann entropy, which is defined like this. It has all kinds of nice properties. So it has chain rules. Basically, it's the right quantity for anything IID. You can think of it as some sort of average case entropy. And here, as I said, it's too good to be true in general. What I mean by this is that, so here we expect, actually small here, we expect something like 2 to the, some constant here times, and then we're going to have like log of Z. So the number of qubits at the output minus some sort of information measure here about this here. And what I mean by too good to be true is that if we try to plug in the von Neumann entropy here, it's just not going to work. It's indeed too good to be true. So we have to go to something else. What this something else could be is the min entropy. And it's defined like this. It has this nice definition. So it's the probability of guessing X by measuring E. It has all kinds of nice properties as well. And in particular, it's a semi-definite program. It's quite well understood. You could think of it as the worst case entropy in some sense. And we'll see that it needs smoothing to be useful in most cases. Now I'll talk a bit more about this later. And here's another definition, and the one that we'll be using here, called the sandwich Renyi entropy. So it has this definition here. The exact form is not so important for us right now. What is important is the fact that it's a family of entropy measures parameterized by some parameter alpha. And if you take the limit of this expression as alpha goes to infinity, you get the min entropy. If you take the limit as alpha goes to 1, you get the von Neumann entropy, and it sort of smoothly interpolates between these two here. And this is what we're going to be using in this talk. And we'll see how very soon. So what do we know already about private simplification? So there's a theorem by Renato Renna back in 2005 that looks like this. So here's so this is what we're trying to define, what we're trying to bound here. And we get this expression here. So 2 to the 1/2 size of the output system here minus H2 of X given E. So this is the sandwich Renyi entropy of order alpha equals 2. So this is our alpha equals 2. So why is this? Why am I not necessarily happy with this right now? Well, it has a few drawbacks. So the first one is that it's not so good even in the IID case. So in the IID case, H2 is strictly less than H, and this is what we expect to be the right quantity in the IID case. So even in this case, it doesn't work out of the box right now. So you have to do something to make it work. And what we usually do to make it work is to do something called smoothing. So the basic idea here is that, first of all, instead of using the 2 entropy directly, we're going to use the min entropy. The min entropy is a lower bound on the 2 entropy, so this is still fine. And then we smooth it. And what we mean by this is that we pick some small parameter epsilon, and then instead of computing the min entropy on the original state, we compute it on the best state that's within a distance epsilon of our state, right? So we look at our state rho and then look at a sphere of radius epsilon in some distance measure. Here's the purified distance, but it's not so important. And then we pick the best one being the one that has the highest min entropy. And then if we do this, we get something like this. So we can replace our 2 entropy by the smooth min entropy here. And then of course we pay a price, which is like the price we pay by just using the triangle inequality, basically. And now what we gain by doing this is that now the smooth min entropy is at least going to give us essentially the right thing for the IID case. And here's why. Right? So suppose that we have an IID state that we're trying to apply private simplification to. We have something called the fully quantum asymptotic equipartition property that says that the smooth min entropy of this thing is lower bounded by n times the von Neumann entropy of 1 of these systems minus something that's small, so order of square root of n. Here. And here I've had the core of the proof of this thing, because it's actually quite relevant to what I'm going to talk about here. And the basic idea is that first we lower bound the smooth min entropy by the alpha entropy, so the sandwich Renyi alpha entropy, and then we pay a price for this. Then we use the fact that this thing is additive on an IID state to get that this is equal to n times h alpha, and then we convert from h alpha to h by paying another price here. And then once we have this, then alpha was a free parameter in this whole thing, so we can just choose it to be this thing. So it's basically 1 plus a little bit. So we just go a little bit above 1 in there in a way that depends on this stuff here. And then we get the theorem. Now the point is, so this works in the IID case. Most interestingly for my talk is that it works in more than just the IID case. So there are other more general settings in which essentially this sort of proof outline works. In particular, there's the entropy accumulation theorem that's used for example, proving security and for DIQKD protocols. The core of the proof works more or less in the same way. And what I'm interested in doing here is basically, well, so we have this proof here where we try to lower bound the smooth mid entropy here by the alpha entropy in order to get a result on private simplification. What if we could just cut out this middleman of the smooth mid entropy and just go directly to the alpha entropy? Like, can we get directly an achievability result for private simplification only using the alpha entropy? So basically, if I go back to something like this here, could I get something that looks like this, but where instead of 2, I have directly an alpha entropy here? Then I wouldn't have to do this whole smoothing business to be able to get there, and I could just basically do this last part of the proof here. So that's what I'll be doing. And in fact, for the IID case, you'll see in the next talk that we can actually do better, and we essentially know optimal results. So this is coming up next. Okay, maybe I'm running out of time very quickly here, so maybe I'll just skip to the main result. So we have some previous work here that you can check out this slide later. So basically, for the fully classical case, this was already known, and we have some partial results for the CQ case and the fully quantum case. Basically, that they work in the IID case, but in the non-IID setting, there's a term in the expression that makes it hard to handle. So here's the main result of my talk. So basically, it's what I advertised, right? So we have an upper bound on this function here for private simplification that involves the alpha entropy directly here. And then there's like the prefactor changes a bit here. We have this thing that doesn't matter. This is basically a constant. And basically, we can do exactly what I said in the previous slide. Like, we can replace the core of the proof by just the last part that involves the converting from the alpha entropy to H here. And then, for example, in the IID case, we can directly get an error exponent just by optimizing over alpha here. And then we can combine this with, in the case of entropy accumulation, to get a result that's, so this is basically the original entropy accumulation result, where we lower bound the smooth mid entropy. And then by combining sort of the part of the proof in entropy accumulation with the results we have here, then we get directly an upper bound on when we apply private simplification to something that comes out of the entropy accumulation theorem. And then we get nicer results. Basically, we get a nice error exponent. And in particular, for those of you who know about the entropy accumulation theorem, there's this probability of the event we have the condition on that enters the picture in a more natural way. So yeah, basically the proof idea uses norm interpolation, a bit like the Riis-Storing theorem. I'm not going to say anything more about this. And yeah, I'm out of time, so I'll leave Kay. I'll turn it over to Kay for part 2 on the IID case. Thank you.
Hi. So, David, can you see my slides?
Yes, everything is okay.
Can I start now?
Sorry? Yes, you should start.
Okay. Okay, now, so the part 2 starts. This is based on a joint work with my PhD students, Yongsheng Yao. We are from Hebei Institute of Technology. So let's look at Frédéric's nice result. One may want to know how good this upper bound is, or can we have a match lower bound or even can we expect for equality here? This is not likely in the one-shot case, but if we would like to go to the asymptotic limit, for example, in the IID city, then it's possible. So in waterfalls, I will show results on the asymptotically optimal characterizations of the speed under which quad tasks go to the perfect. This is the reliability function. A main difference of my talk with compared to Frédéric is that we will employ the purified distance instead of the Trees law distance here. Our results are also given in terms of the salvaged Renyi information quantities. Specifically, we will employ the salvaged specific. I think I needed to share to sorry. Let me. I haven't I needed to open my camera. Okay. So specifically, we employ the salvaged Renyi divergence here. This is introduced in these two papers independently. We also use two induced quantities. One is the salvaged Renyi conditional entropy, and the other one is the salvaged Renyi mutual information. We will use the purified distance, which is the square root of 1 minus the square of the fidelity function. So our first main result is on the smoothing of the mass relative entropy. The smooth mass relative entropy is a basic tool in the one-shot quantum information theory. We introduce its inverse function, that is the smoothing quantity as a function of the entropy quantity. It is known that in the asymptotic city, the smoothing quantity goes to 0 exponentially fast when with respect to the number of the copies of the states. Here we have determined the exact optimal rate of such exponential decay of the smoothing quantity, and it is given by the salvaged Renyi divergence of order greater or equal to 1. This will also serve as a basic tool for our next results. Let's go to our second main result. It is on the quantum probability amplification. So let's consider n copies of a classical quantum state rho xe, and we apply a Hashi function Hn on the x part to extract rather probability randomness. The performance is measured by the purified distance between the resulting state and the ideal state of such a form, either in the average city with respect to universal two Hashi functions, or in the basic city, we define the reliability functions as the optimal rate of the exponential decay of the performance function. And we find that in these two cases, the reliability functions are the same, and they are all given in terms of the salvaged Renyi conditional entropy. This is true when the rate of the randomness extraction is greater or equal to a critical value given here. Our result is derived by know about, obtained by Hayashi several years ago, and our newly derived upper bound, and we show that these two bounds are equal when the rate of extraction randomness extraction is greater or equal to the critical value. Our third result is on catalytic decoupling of quantum information. So we have a bipartite quantum state rho RA, and we introduce a catalytic system A per I in the state sigma. Then we apply a unitary transformation to convert the systems A per I to A1 and A2. And at last, we drop the A2 system, and we get the remaining systems R and A1. We hope that they are in the product stage of such a form. We use the purified distance to measure the performance of this decoupling, and this is minimized over all the possible operations and just described right now, with the restriction that the number of discarded qubits is upbounded by k. In the asymptotic setting, we again define the reliability function as the best rate of exponential decay of the performance function, and we worked out that it is even in terms of the salvaged really mutual information when the rate of discarded qubits is not too large, small or less than the critical value given here. And the result is also determined by derive the upper bound and the lower bound respectively, and we show that when the rate is small or equal to the critical value, then they coincide. Applying this result, we also find the reliability functions for other quantum tasks, such as quantum state merging, split, and quantum channel simulations. And we hope that there will be more applications. So in conclusion, we have derived the reliability functions for quantum tasks. And this is for the first time to give the operational meanings for the salvaged Renyi divergence in characterizing how fast the performance of quantum tasks approaches the perfect. Some open questions is to derive reliability functions for other quantum tasks and for quantum tasks under trace law distances. And Frédéric's talk is actually a major progress regarding the achievability part of this open question. Okay, so we thank you all. And for more details, we refer to the 3 archival papers.
Cool. Thanks a lot, Ke Li, and also thanks a lot, Fred Dupuis, for the 2 very good talks. I'm sorry that we were a bit late, so the next session already starts in 1 minute, but there were also no questions in the chat. So I suppose that whoever has a question for Ke or Fred, you email the question directly to them, and then we move on to the next session. Thanks a lot.
I guess there's the Q&A.
Sorry, that's the Q&A. Thanks, Fred. Yes, okay, let's do it in the Q&A. Okay, and now let's move to the next session. Thanks a lot to the 2 of you.